Hello, welcome to this webinar on Advanced Engineering Mathematics with Maple, the ebook. Now, it might look like this webinar is designed to talk about a book, but that's not what we want to do. What we want to talk about is the idea that Maple should be the tool of first recourse when teaching, learning, doing any kind of mathematics, especially this mathematics that comes after calculus and is needed by engineering students. And it should not be an add-on. The approach that says, learn this stuff by hand and then, oh yeah, Maple can do it too, doesn't work, and that's not what I'm trying to get across. What I'm trying to get across is that Maple should be an integral part of the learning process. And I'm going to try to make that clear with a few examples that I've extracted from the ebook. Now, just a thought on the original Addison Wesley text, which is presently out of print. So this is what the book cover looked like. It's out of print. It's now in an ebook version. The book came with a disc in the back that had a Maple worksheet for each of the 273 sections in the book. Here is a page that lists properties of the book and shows where it's available. There's a student manual that contains all of the solutions worked out for which there were answers in the back of the book. So there were about 7,000 exercises in the book, and about 1/7 or about a little over 1,000 of those exercises had answers in the back, and the student manual has worked out solutions for those. Oh yeah, and there was an instructor manual that contains worked out solutions for all of the examples. Now, the ebook has this structure. There's a table of contents, and here is the preliminary matter. There are 9 units. Each unit has chapters. There are 48 chapters in total. Each chapter has sections, and there are 273 sections. So a user of the book would pick from this table of contents where they want to go, and it would take them to the appropriate section. And I will show you what some of those sections look like momentarily. So here are some of the examples that I would like to share with you by way of making my point about using Maple as a tool of first recourse while learning this material. This section treats approximate analytic techniques for solving boundary value problems for ordinary differential equations, and you can see the methods we'll look at are least squares, Rayleigh-Ritz, Galerkin, collocation. Now, this is what one of the worksheets from the ebook looks like. Okay, this is has not been altered in any way. So there is an initialization section, whatever packages need to be installed, and then there is text taken from the print version of the book, and it's placed where necessary within the worksheet. Well, we'll begin with this example, boundary value problem that we can solve exactly. So we'll use it as a template to see some of the aspects of the procedures we want to invoke. And you can see the example is implemented in Maple, and we have an exact solution obtained from Maple. Now, since there are 4 different methods we're going to look at, there are some common preliminaries that pertain to all 4 methods, so let's take a look at that now. We're going to use this template for our approximation. The functions phi1 and phi2 are given here. So this is the approximating polynomial. The residual, which is what you get when you substitute this polynomial into the differential equation. And notice that this approximation satisfies the initial conditions. It's chosen to satisfy the initial conditions. At 0, clearly this vanishes. At 1, these 2 terms vanish, and that x will be 1. So this satisfies the boundary conditions. Plug it into the differential equation. This is what results. If that came out to be 0, then this guess was perfect. It was right on the money, and you have a solution. But it's rarely that this will come out to be 0. So you would like to make this as close as possible to 0. Now, how would you do that? Well, you have 2 parameters, b and c. So you choose the 2 parameters to bring this residual as close to the 0 function as you can possibly get. And that's what the different methods do. They bring this to 0 in a different way. So the computations are worked out here in Maple. You start with a general cubic, then apply the boundary conditions, and you end up with the approximating polynomial that we showed. Plug it in a differential equation. This is the residual that results. So let's take a look at what I call the least squares approach to getting this residual as close to the 0 function as we can. So we do an L2 norm on R. You square it, integrate it from 0 to 1, and that results in this expression. There are 2 parameters, b and c. Choose b and c so that this is as close to 0 as possible. Here is a graph of that expression. You can see there is a minimum someplace, and here we look at a contour plot. So normal equations, you differentiate with respect to b and c, so it's equal to 0. You solve for b and c. Here are b and c exactly. Here they are as floats. This gives you y1 as an approximation to the solution to the boundary value problem. Here it is in floating point form. The approximation is this graph in red, and the exact solution is in black. It doesn't look really great, so let's find out why and what we could do to get a better approximation. Let's dig in and see what it was that we actually accomplished with that calculation. So here's the differential equation. Operator L is second derivative multiplied by E0, and so forth. This is what the approximation looks like. Linear sum of these basis functions. And there's a linearity here that we're going to be relying on. How do we get the residual? We apply the operator to this approximation, and because of linearity we can move the operator past these constants ck, and they work or apply directly to these basis functions. So L on a basis function is a new function. We'll call that psi. Now when we square and add or square and integrate this residual, we get a function that depends on the parameters. We've seen what that looks like already. And then we differentiate that function with respect to the parameters. So what is it going to look like? Well, here's a square, so you're going to get 2r dr dck. But look over here, dr dck. it's going to produce this function psi. So what you are really saying is make R orthogonal in this inner product to these functions psi. That leads to the generalization that orthogonality is the key here, and in the other techniques we'll look at, we will see that instead of making R orthogonal to L on a basis function, we'll make R orthogonal to other functions and see if that improves the approximation. So in the Rayleigh-Ritz technique, we make the residual orthogonal to the basis function, not L acting on the basis function, but directly orthogonal to the basis function. And so in order to do that, we have to evaluate these two integrals. Turns out that we get these two expressions, or these two equations, solving for B and C under that modus of approach. We get B and C to have these values, and we have a second approximation, the Rayleigh-Ritz approximation, and when we graph the exact and approximate solutions, we see we have gotten a much better fit. Now, what about the Glargine technique? How does that approach the residual? Well, in the Glargine technique, basically what you do is you take any set of orthogonal or even orthonormal functions, and you make the residual orthogonal to as many of those basis functions as you can. That means we have to evaluate these integrals. We get these expressions, we set that equal to 0, solve those equations, and now we end up with a third approximation, this Glargine approximation, in which I have used these two basis functions for the orthogonality, which are different from the basis function of the approximation. Okay, we draw a graph, and you can see it's a pretty good approximation. Okay, so in fact it appears to be better than the Rayleigh-Ritz approximation. Now what about this collocation technique? Let's take a look at the collocation technique. We make the residual orthogonal to these delta functions, which means we are evaluating the residual at specific points. And in this experiment, we'll evaluate the residual at 2 points. I can foresee evaluating at multiple points and then doing a least squares fit, but here we'll evaluate it at 2 points, and we'll have 2 equations and 2 unknowns, which will solve for B and C. It will give us our fourth approximation. It is not as good as methods 2 and 3, but better than method 1. So let's compare these 4 solutions. Look at an L2 norm of the difference between the exact solution and the approximate solution. And those L2 norms are listed here. This was not too good for our first approach, least squares. This was Rayleigh-Ritz. This was Glargine with that particular set of basis functions. And this was collocation with the 2 points. Better than the first one, not as good as either of methods 2 or 3. Then finally, there is a collocation experiment which it behooved me to carry out. This is the approximating polynomial. But we know, in this instance, we know the exact solution. So let's look at the L2 norm of the difference between the exact and an approximate. This yp is this function with b and c undetermined. So we have this expression which we would like to be as small as possible. Well, we know how to minimize that, so b and c taking on these two values makes this expression as small as possible, and we end up with this fifth approximation. So we implement these computations in Maple, and then what we're going to ask is, since we know what the best b and c could possibly be, can we work backwards from this best b and c to optimal collocation points? And that's what we do here. We look at this optimal collocation solution. We want to work back to values u and v in the interval 0, 1 that give us this optimal pair b and c under collocation. And so it's just a question of solving the appropriate equations, and we get two values, u and v, and what we observe is they're not uniformly spaced. And so collocation, uniformly spaced, is nowhere near as good as having a method of picking the best collocation points, and that's a subject in itself. But you can see from these exercises that without something like Maple, you're just not going to be able to carry out these computations in a reasonable amount of time. But with Maple here, you can do these experiments, you can experience these results and get insights that you would not get with a pencil and paper. So let's take a look at another example. This time we're going to look at something involving convolution for Laplace transforms. So this worksheet has been cleaned up. It does not look like this in the ebook version, but I've cleaned it up so we can get through this a little bit more quickly. There are initializations that need to be implemented. That's behind that button. And this is really what we're trying to get at. What is a convolution? What does it mean? How do you get it? So I'm going to have an experiment here with these two functions. This function f and its companion function g. And what does f and g look like? We'll draw a graph. So f is in blue. It's a dying exponential that's cut off and goes to 0. And g is one arch of a sine curve. Now, a convolution for Laplace transform can be defined either by this integral or this integral. They're equivalent. You make a change of variables. They're equivalent. What does this integral mean? Can we get some meaning from that integral? So I'm going to draw some pictures here. So here I'm looking at the function f. I'm looking at this integral. The function f when t is 0. So f of minus x. It flips this blue branch over here across the y-axis. It's this red branch, and then it'll go to 0 on this side. As t increases past 0, this red curve shifts to the right, and this is what this animation is going to show. So I'm going to just shift forward to the right. And what's happening here? This function, which is this red graph as this red curve, multiplies g, but g is this arch of the sine curve. The product is that dark green function. The integral computes the area under that function. So this green blob represents the value of the convolution. And if we increase further, you'll see you get more green blob, and then you get less green blob, and then the green goes away, goes to 0. So it looks like the convolution is symmetric. It increases, decreases, and goes to 0. So you get some insight into what a convolution is accomplishing. For some functions, computing the convolution by the integral definition is okay, it works. For instance, the convolution of sine t cos t, you write the appropriate integral. Maple handles it, sine t times t over 2. So that works. Now, our convolution, the f and the g that we've defined, is a little bit more difficult. So using this expression for the convolution integral, let's ask Maple to evaluate that. You know, here's Maple evaluating, and it comes back with a null result. And the problem is Maple needs some assumptions to make this thing work. So rather than tackle that, let's look at the functions f and g. What does the product f t minus x g look like? It's going to be non-zero only when this exponential, even though it's shifted, multiplies this sign. If there's a 0 multiplying, you're going to get 0. So where is this integrand non-zero? Well, it appears that the integrand is non-zero over a parallelogram. That parallelogram is defined by these inequalities. Okay, you need t minus x be greater than 0 but less than 1, so that you are using this function, and you need x to be greater than 0 and less than pi to be using this function. So a graph of those four inequalities looks like this. Here is that parallelogram. It's the green region. The red region is where the integrand is 0. This is the line t equals x. This is the line t equals 1 plus x. So the integration is an x integration for fixed t. So here we are an xt plane. You fix t, you integrate in x. So when t is less than 1, or less than or equal to 1, this is the integral, and the integral goes from 0 to this line, which is x equals t. When you are between 1 and pi, the integral goes from this line, x equals t minus 1, to x equals t. That's this integral. When you are between pi and 1 plus pi, the integral goes from this line, x equals t minus 1, to x equals pi. And that's this integral, and after that, it's 0. Well, this is a piecewise function. Let's have Maple evaluate that. Oop, there we go. Maple has evaluated. This is what the convolution looks like in this instance. Now, even that is a chore. We had to draw this graph, we had to write these integrals. Is there a better way? Is there a more efficient way to come up with this convolution? Well, here's how I'm going to obtain the convolution a more efficient manner. I'm going to make use of the convolution theorem. What is the convolution theorem? The Laplace transform of a convolution is the product of the transforms of the factors. So using that, if you invert, then on the left you're looking at the convolution. It is the inverse Laplace transform of the product of the transforms of the factors. Can we do that? Let's give it a try. This is the Laplace transform of the factor f, the Laplace transform of the factor g. Let us invert the product of those two transforms. If you have an extremely good memory, this matches what we got here by doing it the hard way. And if we draw a graph, we see that our intuition about what this transform is going to look like, it's increasing, decreasing, and it has symmetry. And so with the right tools, you can get convolutions in a very simple manner, especially if you got a tool like Maple, where Maple will compute the Laplace transforms for you. Well, let's do another example. This time we'll be looking at a periodically driven damped oscillator. So again, I've streamlined the approach. There's the initializations, and this is the problem that we're looking at. We have a damped oscillator. Initial value problem. Inert initial conditions. Now, what is the driving function? Let's execute this stuff. Driving function is the periodic extension of this function, g. So what does g look like? This is what g looks like, and this is what periodic extension will look like. So this is a tent, this is a sawtooth. And we're going to drive this system with this sawtooth function. I now propose to get an exact solution by the Laplace transform. I need to obtain the Laplace transform of the driving term, but it's a periodic extension of g, so I can make use of this formula for obtaining the transform of a periodic function by integrating over one period and then compensating by multiplying by this factor. And if you look real carefully, this is the sum of a geometric series, and that's really what happens when you write out the integral. Okay, so let's obtain that transform. Then we have to transform the left-hand side of the differential equation and set it equal to the transform of the right-hand side. I've applied the boundary conditions. Next step is to solve for y, or isolate y, and then you want to invert this transform. Well, this is not an elementary transform. These exponentials make life miserable. So the technique is replace this exponential with a letter like z, and basically do a series expansion in z and transform termwise. So make that substitution, do an expansion, and we're going to get a partial sum of that resulting series. So the resulting series really is the series z minus 1 over z plus 1. This is that Taylor expansion. The factor 1 over s squared plus 2s plus 10 sits out front, and I'm just going to be looking at a partial sum, and I've gone out to z to the 6. Now we got to invert termwise, so we replace z by e to the minus pi s, and as we look at this expression, we see that every term has the factor of this first term. So think of this as an h of t. If you know the the inverse of this factor, call it h of t, and here there are 2's and pluses and minuses, you can make use of the second shifting theorem and get the inverse transform of all of this. So what is this function? Well, it's more than one term, but it's not impossible to obtain. And so the inverse of this expression, this partial sum, is going to be h of t, that's from here. Then you have 2's, because all of these things have 2's, and then you need shift on h, okay, so it's t minus k pi, multiplied by a heavy side. This is the cutoff, it's the heavy side. And this is what that's going to look like. So we have this collection of heavy sides and functions. A little bit messy. It's hard to tell what it looks like until you draw its graph. So there is a graph of the exact solution, exact on at least 0 to 20. And why can I make that claim? Well, what was the first term that we neglected? The term we neglected was an e to the minus 7 pi s. And what would that have resulted in the solution? Well, a heavy side of t minus 7 pi. Now 7 pi is at least 21. So this heavy side that I've neglected and all other heavy sides that I've neglected, they're all 0 to the left of 20. Therefore, this is exact on 0 to 20. And here I'm going to be looking at a solution technique. It's again an approximation technique that I spotted in an engineering, mechanical engineering textbook. It was like a 1936 textbook that I rummaged out from the library. And when I first read this, I said, this is impossible. This is nonsense. And I have tried it, and I realized, no, wait a minute. This actually works, and it's a very strong technique. Approximate the driving term by a Fourier series. Drive the system with partial sums of the Fourier series. The resulting solutions converge rather quickly. Okay, so we need a Fourier series for the driving term. But remember, you need to only integrate over one period. That's why g shows up here. There are the coefficients. Here's a list of the first few. The first one is pi, but then after they alternate, every other one is 0. So here are some partial sums that I'll consider. I'll call them f1, 2, and 3. And then I just add one more term in each case. How good a job do these partial sums do in approximating the 10th function g? Well, f1 clearly doesn't do a great job. f2 is not perfect either. You can see there's discrepancy at the peak and here at the endpoints. And even f3, there's a discrepancy up at the peak, and it's not perfect at the endpoints. But I'm going to use those three functions, f1, f2, f3, as driving terms in this initial value problem. So I need to solve 3 different initial value problems. And here are graphs of the solutions superimposed on the exact solution. Okay, using just f1, solution's pretty close. f2, the solution is very close. And with f3, I can hardly tell the difference between the exact solution and the approximate solution. And so I did at one point look at this in terms of operator theory star norms and all that kind of fancy stuff. And the convergence is strong. And the technique that was proposed in this very old mechanical engineering textbook is a good solution. So again, here is an approximate analytic technique for solving differential equation problems. Well, here's another example. This time we will look at the notion of Lagrange multipliers. Again, I've streamlined the worksheet to make things go a little bit more quickly. The problem statement we want to consider is this: get the extreme values of the function xy constrained by this ellipse. So enter the function f, and then we'll enter the function g. You bring everything over to the left. Use g is the stuff that's left equal to 0. And this tells Maple the definition of g. Well, this is a Lagrange multiplier problem, so let's see how we can access the solution by Lagrange multipliers. So first I'm going to make use of a task template. Now what's a task template? You go up here to Tools, Tasks, Browse, and you get a table of contents of a collection of tools called task templates. Table of contents. So we want to look here in multivariate calculus, optimization, Lagrange multiplier method. Here is the task template. You can insert it to your workspace by clicking either of these two insert buttons. Default content means you get a lot of extra verbiage, and minimal content means you get enough to make the thing work. And I've already got the tool or the task template embedded in my worksheet. So we make use of it, enter F here, enter G here, and the variables x, y here. This button executes a Lagrange multiplier command and displays the information in this matrix form where you read downwards. There are 4 solutions: x, y, the Lagrange multiplier, and the function value. So you see there are 2 places where the function value is 2 and 2 where it's -2. So we have these 4 solutions. Now it turns out that you can access the Lagrange multiplier technique from the context panel. The way you do that is you make a sequence of the functions f and g, and then in the context panel go down to student multivariate calculus, and the only thing that makes sense to inflict on this sequence of 2 functions is Lagrange multipliers. That's in the student multivariate calculus package. A dialog comes up, you enter the variables x, y, and the returns can be one of 3 things: value, detailed information, and a graph. I'll let you experiment with the graph. This is what happens if you return the value. You get 4 points. Now let's do this again. F, G, hit the enter key, and here, student multivariate calculus, Lagrange multipliers, the x and y are still there. Let's see what you get if you say detailed. Well, now you get the x and the y, you get the Lagrange multiplier, and you get the function value. So you get a little bit more information if you select detail. Now, of course, we would want to be able to do this from first principles, and here's one way to do it from first principles. Compute the gradient of f, a Lagrange multiplier times the gradient of g, and set these 2 vectors equal because you're trying to make these 2 vectors collinear. So we have these 2, they're nonlinear equations. We have to adjoin one more equation, g equals 0. So here's a way to do that. So I'm going to reference this list with its equation label, and I do that by pressing Control L, L for label, type the number 1, and that represents this list. And next to that, I want to put the list containing g equals 0. And if I go here to the context panel, I see a join option. And now I have 3 equations and 3 unknowns, nonlinear set. I always found that this was the sticking point. There are no rules for solving nonlinear equations except the rule or the warning, don't divide by 0. So you can't cancel anything. What you do is you factor and use the 0 principle. Factors equal to 0, 1 or more of the factors has to be 0, and that's how you generate all of the solutions. If you bog down here with your students in the solving of the nonlinear systems, because every system is different. What you do is different in each case. They lose the idea of what the Lagrange multiplier method is all about. So here's where it's really useful to let Maple solve the equations until the student is comfortable with the whole idea of Lagrange multipliers. And then if you think solving nonlinear equations is a valuable skill, then you can go back and pay attention to that. But at least you've gotten across the idea of the Lagrange multiplier method. Well, now we want to solve. I should go back here to the context panel, pick the simplest solve, and you see that you've got the same 4 solutions, Lagrange multiplier, x and y, but you don't get the function value. So you would have to do some substitution back into the function f to get the function value. Well, we're looking for some insight into what Lagrange multipliers is all about, so maybe some graphs might help. So here's one graph. It shows in cyan the saddle function. The red plane is z equals 0, and that's where the ellipse lives. And the black curve is the lift, projection, of the ellipse onto the saddle surface. And you can see why you get 2 maxes and 2 mins. Well, that's one graph. Here is a much more important graph. This is a graph of the level curves. In black, we have the level curves of f. In red, we have the single level curve g equals 0. And I've drawn it so that you can see there are 4 points of tangency between the red curve and one of the black curves. So on this black curve, f has the value 1. On this black curve, well, this one up here has a value 3, and this other one here has a value 2. So as you traverse the red curve, you get f equals 1, f equals 2, and back to 1. So right there at that point of tangency is a turning point. That's where the extreme value occurs. So this graph says the extrema that you want are at the points of tangency. But at the points of tangency, the gradients are collinear. And that's the essence of the Lagrange multiplier method. And we can bring that out more strongly with this animation. We have the level curves of f. We have g equals 0. Gradient on g is in red because g is in red. And gradient of f is in black because f is in black. And let's run that animation and see what happens. At a point of tangency, the gradients are collinear. not necessarily always in the same direction, because here they're not in the same direction, but each point of tangency where an extreme value lives, the gradient vectors are collinear. And that's what the equation that we did here, grad f equals a multiple of grad g. Collinear, not equal, but collinear. Lagrange Multiplier method. I dare say this is not something you can do in a paper and pencil book, but it's something you can do with a tool like Maple. Now here's another example. Heat equation. But this is one with time-varying endpoints. So again, I've streamlined this so we can get through it more quickly. Here's the problem. I'll use this schematic to explain the problem. This blue region represents the exterior wall of a house. This is the outside. This is the inside. So the inside, the wall temperature is kept constant. Whatever, heating, air conditioning. I'm thinking air conditioning. The outside temperature varies periodically. This is the graph of the outside temperature. So I'm saying, okay, this is inside. And it's the inside of my house in Terre Haute, Indiana, when I was teaching at Rose-Hulman. And the summers in Indiana can be hot and humid. Typical afternoon temperature could easily be 100 Fahrenheit. Inside, I'd blast my air conditioner, let's say 70 degrees to have a round number. And I'll take 70 as my 0 point. And so I'm saying that the temperature can go up 30 to 30 degrees over that 0 point, so it's 100 out there. In the evening, if you're lucky, the temperature will drop, outside temperature will drop back down to 70. You might get some sleep, okay, unless you're running your air conditioner day and night. So you have this time-varying temperature on the outside, constant on the inside. I wanted to know what was happening inside the wall. What is the temperature profile inside that wall? So here's the boundary value problem I wrote. Heat equation. Initial temperature, 30. So I'm thinking, I haven't been home. Air conditioning has been off. The wall is completely warm. Left end. I come home, I turn the air conditioner on. This wall is immediately and instantaneously at 0 degrees. Well, that's a myth, right? You really need a Robin boundary condition here, but the problem is tough enough as it is. And on the right side, we have this periodic function. So the solution, because the right-hand boundary condition is not homogeneous, is a little bit more complicated than the very first set of problems you look at for the heat equation. So here's the concept of the solution process we're going to follow. This is the boundary value problem. Split the solution U into two parts, V and psi. Run that through the partial differential equation. And what you find is if you choose psi correctly, you can make the boundary conditions that V satisfies homogeneous. Unfortunately, that shifts the non-homogeneity to the differential equation, but at least it makes the boundary conditions homogeneous. And it also changes the initial function. Now, what is the optimum psi? Well, it turns out to be this. What does G turn out to be? Minus psi sub t. What does F turn out to be? It's F minus psi at x and 0. Okay, so with that choice, V turns out to be an infinite series. It looks like a Fourier series. But the coefficients are functions of t. And so these big bn's are functions of t. In order to find those, you first have to express g in a Fourier series with coefficients that are functions of t. And so you can compute those because you know what g is, and so these integrals can be evaluated. The b's will satisfy an ordinary differential equation, an ordinary first-order differential equation, non-homogeneous. And for this, there is a variation of parameters formula that will say the big B's equal. But you're solving a differential equation, so you introduce a constant of integration. You can choose that constant of integration to be these numbers. Now, f is known, so you can compute these numbers, and therefore you will know what the B's are. And if you know what the B's are, you know what V is. And since you also know what psi is, you now know what U is. Well, let's implement that stratagem. I'll call that the algorithm we're going to use. This is f. These integrals will give us the little b ends. This is g. This will give us the g ends, this integral. Then this is the variation of parameters formula for that first order differential equation, and we can therefore obtain the b ends. That means we can write down the solution for v, and I'm just going to take an approximation. We have to sum the bn's, these are the little bn's, times these exponentials. Now, if you think about this, this is n squared. It's not going to take very many terms before this exponential is really small. So you don't need very many of these terms. So I've taken 5 here and 10 here. And then you just tack on this psi function, and you have an approximation to u. And what remains is to draw some graphs. And if you couldn't draw some graphs, you wouldn't know what these symbols were telling you. And you would not be able to draw these graphs without some kind of graphing device. So I've picked a value for the constant kappa. And I've drawn a graph of the solution. And I've gone between 48 hours and 96 hours. So we're approaching steady state. And you see that the temperatures inside the wall are not constant. And here's an animation of what's going on inside the wall. Here, let's just run that animation here. And you can see that it's going to go up and down. That's what these lines are telling you. The surprise for me was I was thinking that the temperature in the wall would be a constant, linear, and I would have the straight line going up and down. The fact that the temperatures in the wall behave non-linearly like this was something I never expected, and I would never have found out without having a tool like Maple to do a calculation like this. And finally here, I'd like to point out that in the actual worksheet, the derivation of this process is contained just the way it would be in a textbook, but calculations are embedded in the worksheet. So any place where there's a need for calculations, they take place. So the derivation of this process of splitting the solution, etc., shifting the non-homogeneity, and then obtaining a solution, it's all worked out here. the way it would be in a textbook, except where there is a need for some computation. The computations are embedded in the worksheet. So this looks more like it did in the worksheet. I just kept it together when I streamlined the computations so that they wouldn't take an inordinate amount of time for us to go through. For a last example, let's take this compound plane pendulum problem. Again, it's been cleaned up so it flows more quickly. Initializations. And what is the compound plane pendulum? Well, we need a picture. Two rods and two bobs. Arranged as you see here. There's a fulcrum. I put my origin at the bottom. When the pendulum hangs down at rest, the length up the y-axis will be R1 plus R2, where R1 and R2 are the lengths of the two rods. When these swing, there are two angles defined, U and V. The coordinates of the first mass, x1, y1, and the coordinates of the second mass, x2, y2. There are two position vectors, one to the first mass, R1, and one to the second mass, R2. And what are those coordinates? Coordinate for x1 is R1 sine u. You can see the right triangle you would get if you drew a horizontal line, and this piece is R1 sine u. Then this piece is the full height, R1 plus R2, less this piece, cos R1 cos u, and that would leave you this amount, which would be the y1 coordinate. Then with respect to x1 and y1, x2 and y2, you can calculate as r sine v and r cosine v. So here are the coordinates of the two bodies. Now we're going to use calculus of variation approach, Euler Lagrange equations. So we need kinetic energy and potential energy. To get kinetic energy, we need derivatives. Those are velocities. We need then the kinetic energies. Total kinetic energies, the sum of the kinetic energies of the individual masses. We need potential energies and the total potential to two masses. And then the Lagrangian is T minus V. So there's the Lagrangian. Now the Euler Lagrange equations can be obtained in Maple with an Euler Lagrange command. That's this command here. And I've applied a little bit of simplification. What gets returned by the Euler Lagrange command are not only the Euler Lagrange equations, but any first integrals that it can find. And those first integrals will have the constant k in it. So I have removed anything that looks like a first integral. That leaves me with two equations, which I pick out in a specific order because the order can change. And these are the two equations. 1, 2. Nonlinear. Now, there isn't much you can do if you're working with a pencil and paper. Probably you would linearize. So let's linearize. And in order to then draw graphs of whatever solution we might find, we give things values, simplify as much as we can. So let's make the masses equal to a common mass m, and the rod lengths equal to a common rod length r. That's what this step does. Then we have to linearize about u and v being small angles. So sine of u and v go to u and v. Cosine goes to 1. Derivatives go to 0. So these are what the equations will look like when we make the simplifying substitutions, and this is what they will look like when we linearize. So there is an R and a gravitational constant G, and if you have enough patience, you can actually solve this pair of equations with a pencil and paper. It's not pretty, but it can be done. But I'm going to make a further simplification. I'm going to take R1, and then, unholy of unholies, I'm going to set G equal to 1, a gravitational constant. Oh, look. Shift the time scale, move to another planet where G is 1. I only want qualitative information. So let's see what the equations look like. Now, this is about the simplest you can get the equations. They're second order, coupled, linear, constant coefficient. It's possible to solve those. I'm going to solve them twice with two different sets of initial conditions. First, I'm going to swing the top mass to the right and then swing the bottom mass to the right of that. Then let it go. No velocity imparted. Alternatively, I'm going to swing the top mass to the right and the bottom mass to the left. Again, just let it go. So these equations can be solved in Maple. They look like this. You can see fundamental frequencies, and you take linear combination of these fundamental frequencies. But what is this system doing? Without a way to graph these solutions, you don't know what they're doing. So when you swing the two masses in the same direction, the pendulum seems to oscillate together. The two masses seem to oscillate together. And when you start them out with opposing directions, they seem to oscillate in opposition. It would be nice to have an animation of this. So let's see if we can get Maple to animate that for us. So here's an animation. Just run it here. On the one hand, it looks like the pendulum is oscillating in unison. Two bobs oscillating in unison. And here they are oscillating against each other. Okay? So this is linearization and having Maple do all the grunt work of solving so that you can draw these graphs and see the behavior of the pendulum. Now here's something that you can do with a tool like Maple that I couldn't do when I was teaching this stuff without Maple. And years and years ago, I can remember teaching this without Maple. So let's solve numerically the nonlinear equations. So this is a reminder of what the nonlinear equations look like under the assumptions that R is 1 and G is 1 and so forth. As a reminder, this is what the linearized equations look like. Now I'm going to take a numeric solution, desolved numeric, of just the one initial value problem, the one on the left-hand side where the two masses swing together. I'm going to solve that system numerically. And what I want to look at is this claim that when I linearized, I neglected terms that were small with respect to the terms that I kept. And I could never actually see if that was true or not. I mean, I made the assumptions of linearization. how big are the terms I'm neglecting and how big are the terms I'm keeping? Could not do that without a numeric solution. So these are the terms that are neglected, and I've graphed them, and the scale is on the order of 1,000th. And here are the terms that are kept, and these are on the order of 2/10. And if you draw the graph of these two together, terms kept, and look how much smaller the terms neglected are. So here is some insight that I could never have gotten without a tool like Maple to easily and simply do a numeric solution and draw the resulting graphs. Now, one of the things that I've been suggesting is that with a tool like Maple, these calculations are easy to implement, and I would like to show that these solutions of these differential equations can actually be done in a point-and-click fashion. So here is the linear system that we solved exactly. So if we go to the context panel, we see in the context panel two options: solve the DE, which would give me the general solution, or solve it interactively. So let's pick that, and what comes up is this point-and-click tool, ODE Analyzer Assistant. Here's the system of differential equations. Here are the initial conditions. And this system can actually be solved symbolically. And we did so. And we can do it point and click. So this is what the solution looks like in a large window. This is what it looks like if we draw the graph. That's one of the functions. You want to get the other one, what you do is you make a copy, change that copy to the other function v, and now when you draw the graph, you get u and v graphed on one set of axes. You can even check this box and you see the dsolve command is the one that gives you the solution, and there's a plot command down in there someplace that draws the graphs. Okay, so you can get the linearized solution, point and click, and you can even get the nonlinear one, the numeric solution, point and click. Here is the system you want to be solving. So again, let's bring up interactive. This system is in place, but this one we solve numerically. Tell Apple to compute the solution, draw the graph. I think I hit plot options there. Well, let's just put both solutions on right now. Now when we say plot, we will get both graphs drawn at the same time, and you can get the commands for that and so forth. So not only do you have a tool that does work that would have taken hours to do formally, but you can do it in a point-and-click fashion where you wouldn't even have to look up the syntax. You would be able to do it syntax-free.